Good morning, good afternoon, good evening. Thank you all for attending and welcome to the webinar on UL4600, Standard for Safety for the Evaluation of Autonomous Products, a technical overview. My name is Deb Prince and I am the Program Manager for UL4600 and the Standards Technical Panel Chair. I am joined today by Dr. Philip Koopman of EdgeCase Research, who has led the drafting within the Standards Technical Panel, or STP. Before we head into this webinar, I'd like to take a minute to thank the STP 4600 members who have committed considerable amount of time into molding UL 4600 into the document that is currently out for preliminary review. A complete list of the questions and answers will be posted after the meeting, along with a recording of this session. So why UL? Underwriters Laboratories have been developing safety standards since 1903 and have published more than 1,700 standards extending its global public safety mission. UL developed safety standards using an accredited standards development process, which is based on pillars of consensus, openness, due process, transparency, timeliness, and continuous maintenance. With continuous maintenance, UL 4600 can be updated as technology advances or learnings from the use of the standards dictate without waiting on a revision cycle. And some revision cycles, as we know, can be as much as 3 to 5 years. Our STPs are balanced consensus bodies with representatives from a diverse interest categories such as manufacturers, supply chain, commercial users, governments, consumers, testing organizations, international participants. The STP is responsible for the development and maintenance of UL 4600. Stakeholders provide a diverse perspective and expertise and are essential to the UL standards development process. With participation from the STP and stakeholders, the end result is a collaborative consensus standard. Underwriters Laboratory announced in July of 2018 the intention to develop an ANSI UL 4600. A small task group developed the initial draft of the document. The STP met in July of 2019 to further edit the draft. In total, the STP has reviewed and further refined UL 4600 3 times, and now the document is out for preliminary or stakeholder review. The preliminary review comments are due November 1st. With that, I'm going to turn it over to Phil.
Thanks, Deb. And I'd also like to express my thanks to the STP for the supportive environment, the many discussions, and we've received almost 1,000 comments from the STP on the previous drafts that have been addressed in the current draft. I'd like to do a technical overview, and that's going to include an orientation to the current preview draft version of the standard. It should be noted that the contents and organization are likely to change, but I think that the content is pretty close to what we have in mind for there to be in the standards. So we're hoping to get comments to make sure we haven't missed anything or to see if there's some issues that need to be worked out. I'm going to talk about the UL 4600 scope, which to emphasize is for fully autonomous vehicle AV operation, which means no human driver, no human supervisor, no human involved in the dynamic driving task. I'll talk about the main principles, including a safety case being front and center, and also at the end a guide to review and comments. And I'll just mention up front, it's really important when making comments to use the spreadsheet format that is provided, and Deb will talk about at the end to make sure that we can manage the comments we expect to receive. The goal of UL 4600 is to have a structured way to argue that autonomous vehicles, AVs, are sufficiently safe. It's a non-prescriptive approach to the technology and development, and it says, here's what needs to be in a safety case, here's how your safety case needs to be formatted. The idea is to trace all the safety goals or claims to evidence. And safety goals are meant in a very generic sense there. And to do this, use a safety case, but you need some checks and balances to make sure the safety case will be complete and reasonable and accurate. And that's accomplished through 2 directions. One is self-audit, and the other is an independent assessment. There's monitoring and feedback that happens from the field to detect invalid assumptions in the safety case and discover any gaps in coverage. We expect these systems will be deployed imperfect. In fact, that was always true of any system, but with these systems, it's more front and center that we're going to have assumptions and incompletenesses, and so it's going to be essential to really monitor aggressively field feedback. It requires a system level and life cycle approach. Drivers do more than drive, and all the things other than dynamic driving tasks that humans typically do is going to have to get covered somehow. It doesn't necessarily have to all be automated, but it has to be included in the safety case to make sure nothing slips through the cracks. And that includes things like fault recovery, supply chain issues, expected misuse, and so on. And one of the big features of UL4600 is that it has extensive reference lists to improve completeness. And again, there's no way the standard will ever think of absolutely everything, but there's a floor that we can put in to make sure that various teams aren't missing things that are obvious or that other teams have found out the hard way. And so this is a way to sort of set the bar up to a reasonable level to make sure everyone's doing a reasonable job. That's done with prompts and epistemic defeaters. We'll talk more about that later, but the simple version is, did you think of that? Lots of lists of did you think of that? There is an ability to argue that some prompts are not applicable. So just because something is in the list doesn't mean you have to do it. It means you have to consider whether or not it's relevant to you for your safety. In other words, the safety case has to either argue it's been handled or argue it does not apply. So why UL4600? There are existing safety standards, to be sure. I've spent years dealing with many of them. But the UL4600 is primarily inspired by the needs of autonomous systems. They have unique needs. There's no human supervision, and they're operating in an unconstrained environment, things like that. They're non-deterministic, and so on. Now, this version of the standard is for highly automated vehicles. UL4600 is, in fact, intended to be a more generic product standard over longer periods of time, but for this particular version, it's all about the highly automated vehicles because that gives a concrete starting point and it's a pressing need. A system-level approach is needed. There are functional safety standards, there's SOTIF, there's road tests, there's simulation. These all play a role. But the role that 4600 plays is it's a framework to put the pieces together and make sure there's no gaps. Because it deals with a safety case and how to do a well-argued safety case, it has the ability to adapt as the technology evolves. It doesn't say do a particular technology piece. It says here are some pieces that seem relevant for most of these systems. You should do the ones that make sense, and the ones you skip, you should explain why. But that means as a new piece of technology or a new technique becomes available, it can simply be added to the list of things to consider. And if an old one becomes obsolete, you can just argue it's obsolete. So the standard is able to flex much more than a prescriptive step 1, step 2, step 3 type of standard. It tries to cooperate rather than compete with other standards. So it can accept work products from ISO 26262, ISO PAS 21448, etc. And it is designed in a way that you can use those standards if you like, but it does not require them. You can use some other safety standards, but all those safety standards tend to have a process that produces work products. And 4600 allows you to talk about the framework that these work products go in to make sure you didn't miss pieces. The goal is guidance on, is system engineering rigor sufficient? In particular, sufficient to be acceptably safe. I mentioned it's a goal-based approach. Let me talk about that for a couple minutes. Traditional safety standards are prescriptive. Here's how we do safety. They define a process, they define work products, and so 26262, 21448, IEC 61508, MIL Standard 882, the list goes on. Most of them tend to say there's going to be a V process, and here's the steps, and here's the work products, and so on. We're not looking to change any of that to the degree it works for AVs. So if you can use one of those standards and do everything you need to use for AVs, that's great, and UL4600 is not going to stop you from doing that. But there are some aspects of AV safety, particularly machine learning, that are going to be a problem, and the goal of UL4600 is to allow those other aspects to come in, even if your methodology isn't a V. 4600 would still provide you a way to argue that it's going to be safe as long as you've done all the things you need to do. So UL4600 is a goal-based standard. It's be acceptably safe. And to do that, you have to have a safety case, which is a structured argument, and you define what safe means. Here's what it means for us to be acceptably safe. You then have to argue that sure enough, our AV does what we said we needed to do, and what we needed to do actually is going to make us acceptably safe. It does not prescribe any particular engineering approach, but it does say you should do all the good engineering practices. So for example, you're not allowed to skip test. Testing has to happen, but it doesn't say how you have to do tests. It says you have to argue you've done enough tests and that the tests fulfill a particular role in the safety case. It does require a minimum acceptable set of topics. For the safety case, we're going to see more about that later. But for example, you have to identify the hazards that can lead to risks. And that's required, and it's because it's hard to believe that someone can be safe without ever having sat down and thought about all the things that can go wrong. It requires the use of a good system engineering process. It does not require the V, but it requires that in your system engineering process, all the things that tend to happen in a V get covered one way or another. So it's flexible in how you go about it, but it says you still have to cover the bases. And by the way, here's a minimum set of things you have to cover to be complete. So what's a safety case? I've mentioned safety case several times, and I'm using the term the way it's generally used in the safety community, but it's a structured argument backed by evidence. And typically it has goals, it has arguments, it has evidence, although there's no particular terminology required, so you can use goal structuring notation if you want. You can use CA, you can use whatever argument style and structure you like. But you have to define the notation so that someone else looking at it can read what you've done, and it has to be well-formed, it has to be complete. Just as an example, so that people get the idea, you might have a sub-goal or claim that the AV will not hit pedestrians, and you might have some arguments, and these are just some example sample arguments. The AV will detect pedestrians of all types. The AV will stop or avoid collision of detected pedestrians, so you're going to detect them, you're going to avoid them, not hit them. And by the way, there's the possibility that some pedestrians are difficult to detect, and we've spent some time mitigating that risk. So those are the arguments, but you can't just say, well, we're sure we're going to do it. You have to have evidence. And so you might have evidence of, here are results of detect and avoid tests. Here is analysis of coverage of different types of pedestrians. And here's some reliability growth data showing that our pedestrian coverage is improving over time, and we're pretty sure we're to the point we need to be to deploy. I tried to put the UL4600 scope in one picture. It is of necessity going to be high level and missing a bunch of things, but here's one way to organize all the pieces of UL4600. In the top left, you have to define a context, so you need to know what the ODD is, but you also need to define the engineering process and especially the safety culture. Going to the top right, you have to identify hazards from all sorts of things across the life cycle, not just obstacles on the road, but things like what if there's a maintenance and inspection problem. Then at the bottom right, you have to mitigate the risks that are caused by those hazards and by system integration, things like this. And that includes feedback to manage unknowns. And then bottom left, that all ends up being incorporated in a safety case. And there's some things you have to do to make sure the safety case is well-formed and valid, and that includes things like metrics and audits and independent assessment. So these don't quite map exactly to the chapters. The chapters in the standard are more organized along skill sets. But this is an attempt to give you an idea of all the pieces that have to come together to make a safety case. There are some things that are out of scope for UL4600, and what's in scope is just as important as what's out of scope. 4600 does not attempt to do advanced driver assistance system features because those involve human drivers. It does not do AV testing safety because, again, a lot of times, typically the safety hinges on their human driver will do the right thing, and that's out of scope for the standard. But BSI has a new PAS 1881 that is talking about that topic, so we don't do it in 4600. It also doesn't do ethical guidelines. So the IEEE P7000 series, in particular P7009, tries to talk about that. So UL4600 says that you should think about that. You have to decide what your policies are, but it does not attempt to provide guidance as to which policies would be good policies and which ones would be bad ones. It just says you have to define them and put them in the safety case. So human factors are a big piece of safety for systems that are not fully automated when they drive. And that's out of scope. It's a different skill set. It's a different look at the problem, and it's just too much scope to try to put that into 4600. So things like, can the human driver or supervisor pay attention, are out of scope. How to argue that humans are going to behave the way they're supposed to is out of scope. For example, are they going to be distracted when they're supposed to be supervising? That's out of scope. And how to argue a human safety supervisor has enough time to accept a handoff and take over safely with situational awareness. All those things are out of scope. Now, there's an interface between the vehicles. So if you build a system that sometimes is operated by humans, sometimes is autonomous, there is a handoff, and the vehicle side of that handoff is in scope. So things like the vehicle should not spontaneously hand off to a human when it's not supposed to, that's in scope. But whether or not the human is ready to accept the handoff, that's out of scope. So the human factors are out of scope. All the autonomy part is in scope. The details of security are out of scope. There's a requirement for a security plan. There's a section that says you have to have a security plan. It identifies some things that are unlikely to be in an IT-style security plan to add to the hazard list, but it doesn't say what it means to do good security. It does require mapping security and safety to each other using a contract type of interface, but it doesn't go any further. There's a section on security. I expect we'll get many comments about security, but at this point, the sense of the STP is to sort of draw the line that we're not going to try and write a security standard on top of everything else, but we do have to play nice. So suggestions within that scope are always helpful. 4600 has many, many prompt elements. What do we mean by prompt element? So a prompt is used as in with a person. A prompt is a reminder to think of a particular topic. So it doesn't say do a particular thing. It says basically, did you think of that? Did you think of, okay, so you're doing an ODD and you have to consider weather. Did you think of hail? Did you think of what happens when you're operating right at the freezing point and the ice could happen in any second? Did you think about the fact that you might get snow in above freezing weather because the air temperature is colder than the ground temperature? Did you think of this? Does it mean you have to handle it? No, it doesn't. It means these are candidate hazards. These are topics to consider in the safety case. And you either have to handle them with a vehicle, or you have to say, well, my ODD excludes them. That's okay too. Or you could say, yeah, even if they happen, my vehicle doesn't really care because it's just not relevant to me. That's fine too. It's a list of good practices, but also a bunch of pitfalls, a bunch of lessons learned, many of them in other industries, especially aviation, chemical process, places like that. We've learned a lot of lessons, and there's no reason for the automotive industry to have to learn these lessons the hard way. The prompts have to be considered, but not necessarily adopted. So there's a deviation hierarchy here. And so each prompt has one of the following categories. Mandatory, you have to do this. There is no way to deviate. The mandatory prompts primarily deal with either elements of the safety case that just, it's impossible to believe that a good safety case would be missing this. For example, you have no hazards identified anywhere. Well, identifying hazards is mandatory. You have to do it. How you do it, that's a different question, but you just have to have a list of your hazards. Or safety case has to be traceable from the evidence up to the goals. Those sorts of things. Those are mandatory. Required is almost mandatory, and some of the reviewers have struggled with this if they haven't read that section carefully. So section, I think it's 4.1 of the standard, goes in and talks about this, so it's really important to read that before making comments about which category something should be in. Required is almost mandatory. Required means that you have to do it unless there's an inherent intrinsic reason it does not apply. So required is mandatory with an exception of our vehicle just doesn't have that. As an example, if you don't use machine learning at all, then you can deviate from the required MO requirements because you don't use machine learning. If you don't use LiDAR at all, then anything that has to do with LiDAR, sure, you can deviate because you don't have LiDAR. By the way, if you don't have LiDAR, you still have to argue that you can see all the things you need to see. So we don't require LiDAR, but if you have one, you have to do all the required LiDAR things. There is some flexibility in here. Ultimately, you get to argue what it means to be inherently inapplicable or intrinsically inapplicable, but the bar is supposed to be set pretty high, and you're supposed to say, look, this just simply does not apply. Highly recommended is the next category. That one you can deviate with any non-trivial rationale. So there's quite a lot of highly recommended content, and you can just say, yeah, we thought about it. We don't think it applies. Here's a reason. And it might be that there's many, many different types of testing listed, and you've decided to use some but not others because you think the ones you picked cover everything you need. That's fine. If they're all highly recommended, you can deviate from the ones that you're not using, saying we think the other ones cover it. You're done. You're good to go. Recommended is entirely optional. You do not even have to mention them. We just think that they're good ideas to consider. So in your safety case, every mandatory will be present in the safety case. And again, if mandatory doesn't mean you have to add a function to your system, mandatory means your safety case has to address that topic. The required will all be listed, and the deviations will either be, well, it just doesn't apply, and here's why, or it'll be fleshed out in your safety case. And highly recommended, they all have to be enumerated in the safety case, but you can say, we don't think so, and we have reasonable reason. And the assessor, for the most part, is not really allowed to question that reason as long as it's clearly not nonsense. Many processes and technique areas are lightly constrained. So typically, for example, we'll say you have to have hazards. But what about how you identify hazards? Well, there's a section identifying, I think it's about a dozen techniques that can be used to identify hazards. You just have to use one or any other one you want. You just have to say which one to use, but it doesn't say you have to use the one in 26262, for example. So it's quite flexible on process, but in the end, there's some things you have to do. There's a section on operational design domain, which is the infrastructure and the weather and the object and event ontology and things like this. And I'll have some more detail in a second just to explain what we're talking about when we say prompt elements. But you not only have to say, here's what my ODD is, and therefore your safety case can be constrained. You only have to be safe within your ODD. And one of the explanations for deviation is, well, that's outside my ODD. Fine. But you also have to argue that exiting the ODD must be safe. What if you get unexpected snow even though you're in a desert? What if there's something in your ontology that you just never expected and it shows up? What the heck is that? What if you have a catastrophic equipment failure more than you ever thought would happen? All these things can happen. It doesn't mean that you have to continue to operate. What it does mean is you have to argue in the safety case that either they will be so unexpected that it's okay to have an incident, or that you will do the right thing and be reasonably safe when they do happen. So at some point, you have to put together a system-level risk picture, and you have to consider that you'll be shoved outside the ODD through no fault of your own once in a while. That's part of the risk picture. Just to give an example, here are some prompt excerpts from the ODD section. The standard's almost 300 pages long, and this is only some of the things for ODDs, but it says if you want to define an ODD, you have to think about travel infrastructure, object coverage, event coverage, behavior rules, things like traffic laws, and who goes first at stop signs and local customs and justifiable rule breaking. If there's power lines down in your lane, do you go around them even though it's the other lane and cross the W line? Things like this. And so all of these things, the prompt elements, the things in bold, have to be in your safety case. And the examples are not normative. You don't have to address those examples. The examples are there to make it harder for you to forget obvious things, but the examples are also there to define by definition. So vulnerable populations, what do we mean by that? Well, the examples, pedestrians, motorcycles, bikes, scooters. You read the examples like, okay, I know what vulnerable populations means. There's been a conscious effort in this standard to keep the number of words small, because if everything were a complete sentence instead of bullets, this thing would be 2-3 times bigger. So you're supposed to interpret it. You're supposed to have your brain turned on when you interpret it. You're supposed to be a reasonable engineer with domain expertise when you interpret these clauses. There is a section on autonomy. It's structured as an autonomy pipeline. There's no requirement to structure your autonomy in a particular way according to this pipeline. It's just a way to describe the building blocks that tend to typically be around. And so there's a section on sensing, and each subsection just talks about the various types of things that are good practices and the type of pitfalls that are common. So in sensing, it in particular talks about correlated sensor faults, because those are often an issue with safety cases, but many other things as well. For perception, it talks about brittle perception and ontology gaps. For machine learning, there's good practices, good data hygiene. Certainly you have to argue that you're not overfitted. It talks about planning, prediction, trajectory control, and timing. And so each section is a catalog of good practices. some typical bad practices, and you have to argue in each section that that piece will be sufficient to give you system level safety to the way you've defined it. The standard also talks about the system environment and lifecycle. So it does define an item, and that's a 26262 keyword, except we're using it in a very broad sense here. So the item is going to include not only the function inside the car and the faults you consider, not just failures inside the particular mechanism, but the item is going to be the autonomy. It's going to be the vehicle itself. And so even things like tires and wheels are relevant to the degree they can impact the safety case, the degree the autonomy has to deal with it. So for example, if you're going to say, well, we have run flat tires, what happens if someone replaces with a normal tire that's not run flat? Now, that's not a requirement for the autonomy to figure that out, but the safety case has to argue either we're sure it'll never happen because, or if we do get a blowout, despite the fact the tires are never supposed to blow out, or the wheel comes off because somebody forgot to bolt it on properly, we're going to do the right thing, or it will happen so infrequently that it's okay to take that risk. There's maintenance and inspection procedures. Maybe that's how you make sure your tires don't come off, is that somebody's checking to make sure they're firmly attached, and you're sure that inspection will be 100% effective. There's life cycle issues in supply chain, and there's data sources and feeds. So the item has to go all the way out to the maps, to the cell phone infrastructure if you're counting on it, to the machine learning training system, because ultimately all of these things affect whether your final system will be acceptably safe. And therefore, the safety case covers the entirety of the item with all those aspects considered. There's also some assumptions and supporting requirements. You have an ODD characterization, so you don't have to work everywhere, but you have to say where you're going to work, and you have to have a plan, as I mentioned before, for what happens if you get thrown out of the ODD. There may be some road infrastructure support. You may or may not count on that, but to the degree you're counting on those lines to be painted, you have to put that in the safety case, and you have to explain what is going to happen if that's not true, or how you're going to make sure it's always true no matter what. And there may be procedural support, such as inspection procedures, maintenance procedures. And to the degree those are defined outside, that's fine. But the safety case has to define an interface and say, all right, so we're assuming the following things are going to happen some other way. And if those assumptions are violated, we're going to have a way to know that something has gone bad one way or another. So maintenance inspections, I mentioned, there's going to be safety-related maintenance. You have to define what maintenance is required for safety. Are the procedures documented? How do you know it's done effectively? Now, it's possible you may create a system that's almost maintenance-free, and that reduces the burden. But ultimately, there's always something that can happen. Components can fail catastrophically due to physical impact with a low-hanging tree branch, if nothing else. It will snow. Somebody has to remove the snow, and you have to have a plan for all that happens. Now, again, it doesn't have to be automated. There doesn't have to be a robot that crawls around the car wiping the snow off. But you can't operate with snow on the vehicle in an unsafe way. You have to have a way of saying, this is why that will never happen. There probably have to be safety-related inspections. You have to talk about what and when the inspections are required. You have to detect vehicle and infrastructure problems. And you have to argue the inspections really happen rather than just assuming something unrealistic will happen. For example, if a safety case said, well, if one of the sensors is damaged, we're sure a passenger will notice. Well, is that really a good idea? Is the passenger going to do a full walk around of the car if it's raining cats and dogs and it's night? Will they even see the damage? Will they even know what they're looking for? Now, if you can argue that convincingly, fine. But, those are the kind of questions that come up to make sure that the safety inspections will really be done properly. The life cycle and supply chain are also going to be relevant. So one of the key principles of the standard is the item has a valid safety case at all times once deployed. So there's some point in the initial design where you're still building things, that's fine. But at some point, certainly before you deploy on the road, and probably earlier on, at some point you define, there has to be a valid safety case. And once you reach that point, every time you make a change, the safety case updates to track the vehicle all the way through its life cycle. So this is not the type of approach where you say, all right, we ship the car, our work is done, not our problem anymore. In fact, after you ship the car, every time something changes, the safety case changes to track it. And in a world of weekly updates and things like this is going to be essential. Now, when we talk about the life cycle and safety, what are we talking about? Well, you have the requirements design, the ML training, but then you have a handoff to manufacturing. You have What happens during manufacturing deployment? What about end-of-line test safety? Is that in the box or out of the box for the safety case, but at some point deployment is in the box? What about supply chain? What about field modifications? What about operation? What about retirement disposal? And just as a thought experiment, consider, is sensor cleaning fluid life critical? Well, if you get hit by a bunch of mud and your sensor cleaning fluid has frozen, or the reservoir is empty and you used a non-safety rated switch that didn't work, that could lead to an incident. So things like, is your supply chain sending you proper antifreeze, start becoming relevant on these types of vehicles. Now, maybe you can put water in antifreeze and that's okay because you have another plan for if that happens. That's great. But you have to argue out what's the effect of supply chain faults on my system safety along with everything else. There's also update distribution and integrity. You have to do version control, configuration management, not only on your software, but on the safety case to make sure that each car is configuration managed, that its configuration matches a valid safety case at all times. The security of the updates is out of scope. That's in the security standard, but UL4600 says you have to think about security of updates. The role of humans is going to be critical in its absence. So in conventional vehicles, even highly automated but human supervised vehicles, there's a captain of the ship. Even if there's no steering wheel and no pedals, if there's a requirement to have a human safety supervisor, maybe just equipped with a red button, you still have a captain of the ship. As soon as the human is no longer relied upon for the safety of the system, the autonomy has to assume responsibility for all sorts of things that are not just the driving task. For example, interaction with occupants and cargo loading. The car can't take off when someone's halfway into it. The car shouldn't accept a mission start if the cargo in it is loosely constrained and is going to throw around and throw the vehicle off center, or if there's an open container of gasoline that's going to spill out and cause a fire. I mean, all these types of things. Now, does that mean there has to be a camera trying to figure all the stuff out inside the car? No, not necessarily. But you have to argue these kind of things are not going to happen one way or another, either procedurally or with some automated thing or a camera with a person on the end. You can argue it however you want, but you have to argue these unsafe things won't happen, or you're going to have potentially an unacceptable risk. The pedestrians and mobility device users are going to be out on the road. You have to make sure they're safe. You have to worry about other drivers doing crazy things in their cars. You have to worry about special populations. There are going to be people who are sight impaired, hearing impaired, who are not able to speak the local language if you're using written language signs on the outside of your car. All these things have to be considered, and people are going to misbehave. And so, again, you don't have to get all of these things perfect. What you have to do is say, we've considered our ODD. We've considered what's likely to happen. We believe the following levels of risk are acceptable. And then you have to monitor once you deploy because you might have been wrong about those assumptions or the world might change out from under you. You have to talk about humans in the life cycle. Not all maintenance is done perfectly. What's your plan for that? How are you going to know if someone cheated on maintenance or just had a bad day and made a mistake? And if it's life critical, that's a big deal. If it's not, doesn't do extra risk, well, maybe not as big a deal. Ultimately, safety culture for everyone involved is going to be huge to make this work. And there's a section on safety culture requiring that you argue you have an acceptable safety culture. A safety case typically is an inductive proof. You argue, here's a bunch of things, the reasons I believe I'm safe. But it's impossible to ever be complete. This has been known for a couple hundred years. The standard story is the black swan, that every observed swan is white, therefore all swans are white, and the first black swan is a problem. You may say, I'm never going to see a kangaroo in downtown Pittsburgh. You may say that until the day it happens. And so in your safety case, it's okay to say, we think we have everything covered, but there's always the chance that we miss something, because that's the real world. That's always been true of hazard analysis. It's just going to be more upfront and center in self-driving cars. And so what you do is you say, fine, our plan for what if we miss something is we're going to do monitoring. So we have prompts, extensive lists of prompts to make sure it's hard to think of something that is readily thought of. So it's harder to make really egregious mistakes because the prompt lists have huge lists of things that you probably ought to think of. There's also epistemic defeaters. That's an interesting term on safety cases. It's something to go look up, but it's basically these are reasons why your argument might be incorrect. and many of them are in the form of pitfalls. If you do this, a pitfall is if you do X, then bad thing Y is likely to happen. You're allowed to do X, but if you do X, you have to argue in your safety case why Y is not going to happen. That, yeah, we took care of that. And there's some other things, just, anyone who does this tends to have this problem, or even the did you think of that as an epistemic defeater, this is going to work, except what about ICE? What about all these other things? And so the standard spends a lot of time trying to make sure that you've thought of all the things you need to, so there's less chance of a big gap in your safety case. But ultimately, the thing that's going to resolve the gaps is monitoring. Anytime you have an assumption, anytime you have some unknowns, anytime you have potential gaps, you're required to look at what happens in the field, do root cause analysis, and go back and say, aha, there's a hole in my safety case. I'm going to have to fix it now. Ultimately, you will deploy with uncertainty. Again, that's always been true, except that we believe that the uncertainty level will be higher for this technology due to the use of things like machine learning and the complexity of the environment and no human to do the right thing when something bizarre happens. You will deploy believing you're acceptably safe. So when you deploy, you have to argue, we're sure we're acceptably safe, but the catch is, how sure are you? You can't be 100% sure. There's always some uncertainty. And so the model is you deploy when you believe you're safe. There's some uncertainty. You don't even know how uncertain you are, probably because of the unknown unknowns. And the monitoring is used to reduce the margin of belief uncertainty over time. So you deploy thinking you're safe with good reasons, and you monitor to make sure that's really true. And if there's something you didn't think of, you'll over time get better, or the world changes out from under you. You'll detect the world changed and you'll respond appropriately. There's an assessment component. There's an entire chapter on assessment. So the assessment process is part of the standard rather than being a separate procedural document someplace. So assessment is in fact a whole chapter in the standard. And there's two types of assessment. One is self-audit and the other is independent assessment. Now this came after a lot of discussion in the STP because there was an issue that if you just say it has to be external, well, the external people may not know as much as the internal people. And external doesn't necessarily mean that they have all the skills they need, and so on. But if you do it internally, then there's the issue of independence. So where we ended up was a two-phase process. The first one is self-audit. So self-audit is done by people who are members of the team or closely work with them. It may be the safety department in the company, but there are no barriers, no walls, no independence required. These are supposed to be people who are integrated in and understand the technology inside out. They can build, and also, if they like, the same people can audit the safety case for completeness. There might be some separation, but that's entirely up to the developer. And their job is to make sure the safety case really does prove the system is safe, check for reasonableness, and make sure it's complete. And their work product output is a complete safety case that conforms to the standard. And they say, we're sure it conforms to the standard. So between the developers and the self-auditors, they're taking responsibility for safety. The independent assessor comes in. The independent assessor checks to make sure that the self-auditors have done a complete job. So the independent assessor has to be independent, they have to be competent, but they don't have to know the ins and outs. What they have to be able to do is check and say, yep, this is a well-formed safety case. So it's a check and balance on the self-audit to make sure the self-audit doesn't have any blind spots. The independent assessors critically are not expected to find technical defects. They're not the bug police. They're there to make sure the self-auditors did a good job. Now, that's a two-edged sword. The first edge is that the independent assessors aren't supposed to be hassling the team about, well, I think you should have done this other thing because I think it's important. The independent assessors don't get to say that. On the other hand, that means you don't get to blame the independent assessors for having missed something. So this approach, it's always been true that ultimately the buck stops with the developers, and this approach simply acknowledges that and say the developers own safety. The independent assessor is not in charge of safety. The independent assessor is in charge of a well-formed safety case and helping the self-auditors make sure they don't have blind spots. But ultimately, the developers and self-auditors as a team own safety. It's up to them to make a safe system. Now, the independent assessors are going to show up more than once. So if things like the field feedback process, if the root cause analysis is not being done, the independent assessors will pick that up and say, hey guys, you're not doing root cause analysis. And so many safety issues that could happen will in fact be caught via that mechanism that things are happening in the field and they shouldn't be happening. The independent assessors will have visibility into that. But again, ultimately, the developers own safety. So what I just talked about was the beginning of a number of feedback loops. Because it's not possible to have a complete standard and it's not possible to prove safety completely at deployment, they're going to have to be feedback loops, but they're stacked much deeper than is typically seen. So there's feedback loops within a product. As part of the standard, you're required to monitor incidents, not just loss events, but incidents. No one was hurt, no one was injured, but something went wrong. You have to go find out what happened and go back and potentially update your safety case if it's because you missed something. And during assessment, you also have to do reassessment every time you do a safety case update that's bigger than a certain amount. And the standards process also has feedback. So Deb mentioned that this standard is under continuous maintenance. That means every year or potentially more often, if something big happens, the lessons learned from the field are going to be fed back by the independent assessors to update the standard. And so we think that one of the learning mechanisms is the prompt element lists in the standard update over time with new hazards and new issues that have come to light. The standard does have a process to make sure that no proprietary information is leaked. But at some point, something like, oh, we didn't realize that striped shirts tend to confuse perception systems or shirt color is relevant. If one company finds that out the hard way, that's the kind of thing that ought to be put in the standard, and it's not revealing the secret sauce of how they actually built their system. There is support for component assessment. The automotive supply chain is super important. And so there's an idea, basically a system element out of context, a SEOC, although it's either hardware or it could be a pure software component. It can sort of be anything, but it's along those ideas. And it uses a design by contract component interface. So the idea is if you have a separate component you want to buy, hardware with software in it, whatever it is, you can say, fine, I want to buy this component. Now I have to include it in my safety case, but the vendor, the supplier, doesn't want to give me the details of the safety case they used for it. Okay, that's fine. We have an interface. The interface is I provide certain services and assumptions to it. I promise in the hardware world, I promise it'll get a certain voltage and it'll get a certain clock cycle and all that sort of thing. Or the software will have a certain type of interface. It'll never feed it null pointers, whatever assumptions you make. And you have to argue in the system level safety case, that's always true. You're not allowed to just assume it's true. And given those assumptions, the component vendor can say, okay, fine. As long as you meet those assumptions for keeping me fed and happy, I promise to provide you the following services. And there's also some context, for example, the fault model used in the assurances by the component vendor. And the component probably doesn't meet all of 4600 clauses. It probably only meets some, so you have to document which clauses you were assessed against and which you were not. But the result is a conformance report that says, if you provide me the following environment in your system, I promise to do the following things, and I was assessed according to the following subset of 4600. Then you can plug that in basically as evidence that can be used in the argument in the system level standard. There's also change and impact analysis. We expect these systems to continually change. The ODD will change. Maybe you want a bigger ODD. Maybe you find a surprise in your existing ODD. Maybe there's a new fashion style. Maybe the laws change. Who knows? Things are going to happen. You're going to have system functionality updates to correct defects, to correct gaps, to do whatever. Change is going to happen all the time. And one of the big questions is, all right, you're doing all these changes. Do I have to do an independent assessment every time I change a line of code? And the answer is, well, it depends. But there's a process defined, and so part of the assessment process defines exactly what it means to do incremental assessment. Anytime you make a change, even if it's a typo in the documents, you do an impact analysis. Now, if you're smart, you have a process that says, all right, typo in the document that doesn't change the word meaning, we're going to stop right there. We're going to have an easy screen for that. Great, fine. But you have to define that. You can't just assume it. If you have to update the safety case, you update the safety case. When you update the safety case, you have to assess how big the change is, whether it's a big change or a small change. Now, big and small change, that depends on the exact system and your process. So you have to define what big and small means. It's probably not just one line of code is small because it depends which line of code. So you look at the safety case. If it's required to update it, you do an update. You update the self-audit, but you do an impact analysis saying, all right, I made this change to the safety case, but really only a couple things changed. I'll just self-audit that piece and we'll probably be good to go. And then as the output of the self-audit, you decide, again, according to a predefined criteria, was our change big enough that we have to call in the independent assessor? Now, these criteria are defined the first time you're independently assessed. The independent assessor gets to weigh in on whether the big, small change criteria is acceptable. And so that becomes part of your safety case. You're not allowed to change it till the next independent assessment. So you get an outside check and balance to not game that. Additionally, there's likely to be a periodic independent assessment because a number of small changes will probably accumulate to have a big effect. So you can expect, if it's a small change, you just update the safety case, do a self-audit. If it's a medium to big change, the independent assessor comes in, and the independent assessor also comes in periodically because the world moves out from under you. Every once in a while, someone's going to need to take a look. The size of the change relates to the safety case impact, not the number of lines of code. And the impact analysis informs all this. So you can make changes. There is a cost to be paid in terms of reassessment and self-audit, but the cost is proportional to how big the change is in terms of its impact on the safety case. Typical software safety standards, functional safety standards, have the notion of integrity levels. We require an integrity level as well. But there's an interaction between integrity levels and prompt elements, and the prompt elements smell like integrity levels to some folks, and they're completely different, so it's important to get that straight. So to refresh on the prompt element categories, there's mandatory, required, highly recommended, recommended. That's whether or not a deviation is permitted in the safety case. Orthogonal to that is integrity levels. So these are going to be things like ASILs or SILs or DALs, depending what background you have. And there are only two integrity levels required. One is life critical, another is injury. You probably want a third one, which is not safety relevant, QM in ISO 26262. So in practice, you'll probably have three. You can have more if you want. It's designed to be compatible. If you want to use the ASILs, ABCD out of ISO 26262, go for it. That's fine. That's compatible. But it requires a distinction between life critical and injury and not safety related. Now, how does this play with the prompt elements? Okay, well, the way it plays is that the integrity levels tell you how much engineering rigor you have to apply, whereas the prompt elements tell you how much safety case documentation rigor you need to apply, and they're not the same. Let me give an example to try and illustrate that. Let's talk about static analysis. So this is a static analysis checker on your code, and it's looking for compiler warnings, that sort of thing. These are well-known tools. And in the prompt element space, it may be required that static analysis used to some degree. So the safety case may say it's required static analysis. What does that mean? You have to use a static analysis tool unless you can argue that somehow it does not apply to your system. That's hard to imagine. Probably you have to use the static analysis tool, but if you can argue it, good for you. Right? But it doesn't say what you do with the static analysis tool. It just says you have to argue you used one to an acceptable level to meet the risk reduction that's required. Independent of that, you have an integrity level that you yourself design, and your integrity level has the option to say, okay, for static analysis, if I'm life critical, I'm going to use the following type of tool, and I'm going to use the following very aggressive, very pervasive warning structure. And for injury, I'm going to back it down a little bit, and for QM, I'm going to use basic static analysis, nothing more. So the prompt elements tell you what topics you have to cover in the safety case. The integrity levels allow you to define an appropriate level for how aggressive that coverage has to be. So they're independent type things. When people look at the standard and they see mandatory, required, they start thinking that it's like the plus signs in 26262 about that they're mapped to integrity, and they're not. They're completely orthogonal. So how does UL4600 work with others? Well, ISO 26262 is likely to be a starting point. It is not required. You do not have to use that standard to conform to 4600. You can use 61508. You can use MIL standard 882. You can use whatever you want, but probably you're going to use something. And that's going to produce work products, and most of the standards trace to a V. That's great, but V is not required by 4600. You may use 21448 or SafeAd or something else to provide more guidance, especially for the machine learning autonomy part. That's fine too. That'll also provide work products. Ultimately, you come up with a list of things. For example, you come up with a list of hazards. But how do you know the list of hazards is extensive enough? You can use the metric of, well, we spent a lot of time and a lot of effort on it, but 4600 gives you a framework and taxonomy to say, there's a bunch of things we're sure you have to think of. And if you miss those, your safety case for sure is incomplete. Again, you don't have to do them, you have to think about them. So 4600 is your safety case really as complete as it needs to be? And again, there might still be holes. That's why the feedback requirement is there. So you can think of it very loosely as a template for a technical safety report. That if you come up with a safety case and if you elect to make the top levels of it public, then you can say, look, you should believe we're safe because here's our approach to safety. And we had an independent assessor come in and make sure the details we're not showing you actually did cover all the clauses in 4600. It gives you a minimum criteria for complete coverage and feedback. It gives you lists of positive and negative lessons learned that over time can incorporate lessons learned from the environment and from deployment, so every car company doesn't have to learn the lesson the hard way themselves. And it gives you an objective, we hope, repeatable assessment criteria for a safety case. Now, ultimately, the team owns safety, but you have these checks and balances to make sure that everyone has a safety case that's up to snuff for the standard. There's a list of titles to give you an idea. This is an organization I mentioned earlier. It's more based on skill set than anything else, but it has risk assessment and humans and autonomy and classical software and system engineering, dependability, data, tool qualification, and so on. And you can see at the end, chapter 16 is metrics. There is no particular metric defined, but it requires that your safety case has metrics and it has criteria to establish what kind of metrics are likely to help. The really short version is the metric should prove that your safety case is on track rather than just being arbitrary numbers of whatever you can measure. And there's a chapter on assessment at the end, as I mentioned. We anticipate the technical benefits of UL4600 will be that it's a catalog of best practices. It's going to avoid missed hazards. It has lots of hazards in there. I'm sure there's more that are going to come up, and on comments, we welcome all the hazards you can think of, and we'll decide which bin makes sense, as the STP will decide which hazards are you really have to deal with and which ones are just nice ideas. It has a bunch of pitfalls, lessons learned usually from mishaps that happen in other industries, including the conventional car industry, and the mechanism for industry to share without sharing the design details. This objective, repeatable, independent assessment is what we hope will be one of the benefits. There's a self-audit to be a first level of check and balance. And if you miss things, the feedback is there to identify surprises and gaps. The independent assessment is there for a warm, well-formed safety case. I believe that checks and balances are required to actually get to safety. All teams have pressure on them, and it's always nice to have someone independent just keeping an eye to make sure that the team's under time pressure, there's someone independent to stand up and say, no, you really got to do all the stuff you have to do if you really want to be safe. The independent assessor, as much as we can, is not about subjective opinion about whether the developer tried hard enough. It's, here's the standard. Did you actually do all the things you need to do to get through the standard? And we're trusting that, part one, the developers will actually want to be safe. The developer assumes burden for safety, but also those feedback loops are there, that even if the developer with the best of intentions tries to be safe but misses things that aren't in the standard and the independent assessor also misses, that feedback is a way to let you know something's about to go wrong. You better get on top of that before you have a big loss event. And back to you, Deb.
Like I said, the slides will be available. This webinar will be available. The questions, and we'll post answers to the questions that were submitted, are available. The document, again, is out for preliminary review, stakeholder engagement. The comments are due back on November 1st. If you're not already keyed into it, being a stakeholder and access to the document, please send me an email. My email is up there, and again, it'll be on the slides. I can get you registered as a stakeholder. If you have any comments, questions that you didn't type into the box and what you would like about what you heard in the webinar, you can also shoot me a question. We'll do that. And then questions about when you're reviewing the standard. Again, when you're registered as a stakeholder, you will get access to our online system. It's called CSDS, and there you'll have the document and then how we want you to post your comments. It is an Excel sheet on there, and it has the format as shown on this slide. So again, November 1st is the deadline. Takeaway, November 1st is the deadline if you're not engaged. contact me, deborah.prince@ul.org. What happens after that? So what happens after that? We hope to go to balloting in December. We're targeting publication first quarter of the standard. Again, stakeholder engagement, STP engagement. There are questions of, are these stakeholder lists, the people that are signing up to be the stakeholders, is that public? No, the list itself is private. Our STP members is public, the stakeholders is private. However, I want you to know, if you do comment on the standard, that comment and who it's associated to does become public, because again, our process is open and transparent. So with that, I again appreciate your time completely. Apologize that we really could not get to any of the questions and answers, but we will post them as promised, and we'll have that up there as quickly as possible. The slides will be posted today. Again, thank you, everyone.